Hello and welcome everyone to our presentation about defense in depth techniques for modern web applications. There's a couple of really cool features in the browser platform that basically support developers to build like a safety net in case that the primary defense mechanism fail. And, especially for sensitive applications like, Gmail or banking sites, you really want to have some second layer of defense in case something goes wrong, right? Briefly about us, this is Michele, I'm Lucas. We both from Google Zurich. I think it's our third or fourth time here at Hack in the Box. We're always here, super awesome. And we're basically working in a special focus area at Google. So we basically try to fit, mitigation techniques into our products. Like Gmail or these big products, they're here for a long time, and it's not trivial to basically retrofit them and enable some things like CSP or other stuff, right? Yes. So we have a pretty long agenda today. We first will talk about content security policy, because this is something we have been working and contributing to for the last couple of years. And we built up quite some knowledge there. We wanted to share that with you guys. Then we'll talk about subresource integrity, same-site cookies, site isolation, KORB, from origin response header, and then some probably upcoming, very promising new techniques like Suborigins, origin policy, and feature policy. But for now, we'll start with content security policy. I don't know how many of you know about CSP. It has been around for quite a while. I think, almost 10 years. It's really complex, and there's a lot of misconceptions around it. And we basically wanted to bust some myths here and wanted to demonstrate and explain some best practices, how to really roll it out that is like an effective defense, especially for cross-site scripting. So CSP is a response header. So it's basically sent from the server to the client, and the browser takes that header and basically allows the developer to restrict certain features in the web platform for that application. And we use that to basically mitigate cross-site scripting. It is very important to highlight here that this is like not a replacement for careful input validation, and also not a replacement for output encoding. And it's basically a second layer of defense, right? It's not something that you would roll out as your only line of defense. Unfortunately, we might hear that sometimes, right, from pen testers, that they find cross-site scripting and then they report it to the company and they say, oh, we have a CSP, it's blocked by the CSP, but we don't fix the access, right? So yeah, you have to fix the underlying bugs, right? It's like really a second layer of defense. So what is CSP not? I already said it. It's not a replacement for secure coding practices. And it's also not a mechanism to prevent data exfiltration. I have a slide on that particularly later. But this is also a common misconception, which we often see around CSP. CSP is actually super complex. It's, as I said, it's around for a long time, and they kept adding features to the spec. And in the end, it basically can do a lot of things, but not all of these things work. It's not trivial, and it's also not intuitive, unfortunately. So I only had a place on the slide for like 6 use cases. I think there's more. Most promising and most prominent one is probably using CSP as a defense in depth protection against cross-site scripting. You can also use it to protect against UI level attacks, right? There's some really sophisticated attacks with styles you can do. We'll talk about a keylogger, a password keylogger using style sheets later on. So you can use the style source directive to mitigate that. Then there's a couple of things that are basically not really related to CSP, but they basically use CSP as a delivery mechanism, right? So for example, there's like upgrade insecure requests and block all mixed content that is like somehow in the HTTPS realm. It's quite useful, but personally I consider these, not really in the core focus area of CSP. Also, frame ancestors is something that they probably just added to CSP because it's a nice transport mechanism, and you can, you have more granularity of what you can specify in frame ancestors compared to the framing headers. And then there's also some use cases where you basically just want to send a CSP that blocks everything. That can be a mitigation if you're hosting like user-provided content uploads, right? And you basically want to make sure that they basically never execute. Then you could, for example, set the block all header. And last but not least, some people also try to prevent data exfiltration with CSP. Unfortunately, this is doomed to fail, but a lot of people still do that. And I have a slide on that as well later. So I just recommend to you, like, don't even try. In the best case, it slows down the attacker, but it's not a real mitigation, right? So in our talk, we'll mostly focus on the XSS part, because this part is already complicated enough, and we could probably fill like 2 or 3 talks just with these topics here. There is about 3 flavors of CSPs that can be used to mitigate cross-site scripting. There's the very popular whitelist-based CSPs. You basically have a list of hosts or origins that you allow the site to load scripts from. We have been talking about this particular form of CSP in the last year and the year before, and it's kind of inherently broken, unfortunately. So what we usually recommend these days is using nonce-based CSPs or hash-based CSPs. Very quickly about the whitelist-based CSPs, I really don't want to spend too much time on them, but they're basically broken, and there's a research paper which we submitted in the November 2016, and it basically has like a lot of bypasses for whitelist-based CSPs in general, and we basically found out that like with some list and some rules, you basically can bypass like almost 94% of all the web's whitelist-based CSPs. Like we used the Google crawler and crawled like for all the policies we could find, and they were really not strong mitigations, unfortunately. So what we propose instead is using nonce-based CSPs. They're quite different compared to the whitelist-based ones. They basically are, what is really nice, they're always the same for every site, so you don't have to come up with a new CSP for every deployment. You basically just have a nonce token that changes for every response, and that should be unguessable by the attacker, right? Like an XSRF token. So the idea is the token is the random number, the random token is in the header, and the random token also has to be in every script tag on the page as in a nonce attribute. And only if the nonce attribute matches the nonce value in the header, that script will be executed. It's really nice because it's significantly less fragile than the whitelist-based CSPs, because with the whitelist-based CSPs, you have the problem that, if some path changes, your site breaks, right? The nonce-based CSPs is much more robust because you basically nonce the script text directly, and then it doesn't matter if the content changes or the source where the script is loaded changes. And it also does not have all the whitelist-based bypasses, which is a really nice feature. Super quick recap, how does a nonce-based CSP work? On the left, we have money.example.com. It is served with this content security policy, which restricts script source. And the browser basically allows these 2 scripts to execute, like it's an inline script and a source script. They both have the correct nonce attribute value that match the header value, so they execute. An attacker, on the other hand, does not know the nonce value in the header because it's basically a one-time token, right? Every response has a new value. So he can not inject a script with the correct nonce tag and nonce attribute, sorry, and the browser will basically block these executions. That's the basic idea behind it. So what's the problem? Nonce-based CSP is actually around for a while now, but it is almost not used in the public. The big problem is that it is very, very hard to nonce every single script tag. Especially, it is hard if you don't control the entire JavaScript landscape, right? If you load Google Analytics, if you load a Twitter widget or a like button or something that you source from a third party, you basically don't control if these sourced scripts then load child scripts, and you basically cannot nonce these child scripts, right? Because the source code is out of your control. You load it from a third party side. So that breaks. If it breaks, you cannot roll it out because, I mean, it's a defense in depth mechanism and you want to have a functional application after all, right? So strict dynamic is really, really useful here because it transitively propagates trust from initially trusted scripts to child scripts over certain APIs. This is really a game changer. So you'll see later on the slide, we basically, because of that, we were able to roll out the strict CSP policies which are nonce-based on over 50% of all outgoing Google text HTML traffic, right? Which is really massive, right? Because it's like a lot of applications. And with the previous whitelist-based model, which was even also insecure, that would have never been possible. Yes, so this is how strict dynamic works in theory. The green box shows a script tag in the HTML markup. It is nonced because it comes from the server, right? But this script then creates child scripts via document create element and then later document body append child. And usually without strict dynamic, this script would be blocked from running because it does not have the nonce attribute set, right? But because of strict dynamic, it is allowed to run the child script, the bar.js. And this basically makes like module loading work, like widgets work, and it's really useful. At the same time, prominent or like very common DOM XSS patterns like document write and document body.innerHTML or internal innerHTML is not allowed to create scripts, right? Because they basically take unparsed text and, that's a very common it's a very common reason for cross-site scripting DOM XSS. So this is great, right? It allows you to roll out a CSP. There's one culprit here. You really need to make sure that in this case, this parameter, the script.source, is not user controllable, right? Because if the user can control that, it basically bypasses the CSP. That's a trade-off for making it deployable, but it is a good trade-off, in my opinion, because you basically get rid of reflected, stored, cross-site scripting, and the big portion of the DOM XSS, right? So it's strictly better than not having a CSP. So as I said, it can get pretty confusing. So if we dive deeper only on the nonce and hash-based CSPs, we can have like a pyramid with different levels of security guarantees, and on the one hand, and the different levels of like deployment difficulty on the other hand. So at Google, we basically use like these level 1 policies mostly. These are like nonce-based CSPs with strict dynamic and unsafe eval. The nice thing is, especially in our case, it's really easy to roll them out because we have very good templating systems that are context sensitive and that basically automatically nonce all the script tags on the page. So quite often it's just a matter of like turning it on the framework and it works out of the box. And it gives us some pretty good guarantees for the amount of work required. As I said, like stored reflected XSS is mitigated, XSS through like JavaScript UIs is mitigated, and most of the DOM XSS vectors are mitigated. Since most of the Google applications are based on Clojure, we did not have any strict dynamic bypasses on a Clojure application yet, which is also quite good. But, ideally, we would move up the pyramid, especially eval is something I really dislike. And we are basically working on like refactoring the usage of eval such that we can basically block it entirely. Because if you remove unsafe eval, you basically also get rid of the attack vectors that are based on like putting user input into eval. And then in rare cases where you really control the entire JavaScript stack, right? And where, I don't know, maybe new applications, you can try to have a nonce or hash only policy without any strict dynamic. But it's really restricting because you cannot use any third-party widgets or anything else, right? But some applications can do it. And yeah, on the right corner, I put whitelist-based CSPs because they're almost impossible to get right. There's some exceptions to that rule, but I would not try it. This is basically how it looks like. We use this base policy. We also restrict object source and base arrive because that would be common bypass patterns. And if you go up the pyramid, these keywords get removed, like unsafe eval and strict dynamic. Yes, we also wanted to update you with some new upcoming features in CSP3. There is unsafe-hashed-attributes, which is coming. It's really interesting because you often have the problem that if you roll out a useful CSP that does not have unsafe inline, you have to remove all the inline event handlers. For example, onClick do submit, or some use like link tags with JavaScript equals void 0, or JavaScript :void 0 for backward compatibility to make a link tag rendered as a link in all browsers. And first, it can be a lot of work to refactor these, but that's not the problem. The problem is if you have some third-party code that creates elements with inline event handlers, you basically cannot enable CSP because these will break as well. And unsafe-hashed-attributes basically expands the concepts of hashes for CSP to these inline event handlers. So in this case, you basically generate the hash for do submit, and you add it to the policy, and then this one would also be allowed to execute. It does not have many downsides, but in theory, you could reuse these event handlers. Like you could inject a new tag that says, a new image tag, and that says on error do submit. So that is something that is possible in this attack model, but you would not get direct script execution, right? But you could build interesting constructs. But one really cool thing about that is that this is the first time that basically allows you to generate a CSP on the fly. So if you, for example, have a static content that is not user influenceable, you could basically have a proxy that nonces all the script tags and hashes the inline event handlers. And by that, you could basically restrict a big portion of the DOM-XSS attack surface of like static content sites, fully automatic, without having to manually refactoring them. This is something we're very interested in, and we'll, try to deploy in the coming months. So we haven't tried yet, but it might be promising. And then there's another interesting one, which is unsafe inline attributes. This is not spec'd yet, but it's a proposal. It came up again because very recently there was a CSS keylogger that used style sheets, like selectors, to steal passwords from input fields. And it's actually really cool what you can do with CSS, right? So if you have the cycles, you can also try to restrict style source, right, with CSP. But in some cases, it's even harder than restricting script source because it is extremely common to use inline styles, right, on pages. And refactoring all of these is a lot of work. And again, if you have third-party widgets, you cannot refactor it, right? So what you can do is with unsafe inline attributes, you can basically blanket allow all inline styles. That's not great, but there is a significant improvement over unsafe inline in general, right? Because if you just have unsafe inline, it's like if you don't have any protection. If you have unsafe inline attributes and still hash or nonce the actual style blocks, it is an improvement because in contrast to scripts, the style attributes are actually significantly less powerful than the style blocks. So you don't have the selectors in the style attributes, so you cannot carry out these kind of fancy attacks with CSS, which very often rely on very powerful constructs like selectors. So this is one attack vector you could mitigate with that. Ideally, you would just refactor all the inline styles and just hash or nonce all the style blocks. But, it might be a stepping stone to go there. And one slide on why we don't recommend to use CSP to prevent data exfiltration. We added this slide because we have seen this quite often, and it's usually not a good idea because the TLDR is once you have a JavaScript execution, you can basically, you basically have the whole web platform at your hands, right? And it's so powerful, and just so many ways to exfiltrate data once you have JavaScript execution, that it's basically, CSP is not powerful enough to prevent that, basically. So one very trivial example is attacker could just write a link tag with the document cookie in the path, and then click that link. CSP cannot restrict navigation, right? So even if you block everything with your CSP, there's like no way to prevent this data exfiltration once you have script execution, right? And there are other examples like post message, DNS prefetch, window.open, and others. So the goal is really to prevent the script execution in the first place, not to prevent data exfiltration once someone has a script execution, right? So 2 slides about CSP at Google. I already mentioned during the last 12 or 18 months, we basically were able to ramp up CSP coverage to over 50% of all the outgoing Google traffic, like text HTML Google traffic. And we focused on sensitive stuff like account login, Gmail, Docs and Drive, and stuff like that. And we're not there yet, right? There's still a long way to go. But the goal would be to basically enforce it on all new launches, and especially in all the sensitive applications. And we're also investigating how we can get rid of unsafe eval. We basically have it in some core libraries that are loaded almost everywhere, so we cannot remove it at the moment, but we're trying to change that. And also in some places, we're experimenting if we can get rid of strict dynamic, but that's very hard and only works in some cases. We have a couple of cool tools that we use also internally and that are open sourced and externally available. There's the CSP evaluator. You basically paste the content security policy and it tells you if that policy is useful to mitigate cross-site scripting. If there's anything red, it's usually a bad sign. And internally, we also have very powerful tools that basically monitor the CSP coverage of outgoing traffic, that crunch together like the millions of CSP reports we receive, deduplicate them, and provide like actionable items for developers, especially in the rollout phase, to remove CSP blockers like inline event handlers, or if someone forgot to nonce a script or something like that. And with that, I'm handing over to Miki to talk about subresource integrity.
Awesome. So that was CSP, right? It was the top mitigation against cross-site scripting. We'd like to introduce you some other mitigations that are part of the web platform. Not all of them are implemented, and I would say which browser support which. But they are very interesting, and some are very low effort to implement in your websites. And so we would really like to see the adoption of some of them to actually increase in the wild. So, for example, one such example of an easy mitigation to adopt is Subresource integrity, or SRI. Basically, a lot of websites have to source external scripts with a script tag from a third party, usually a CDN. And the problem with that is that you are executing in your web origin basically untrusted JavaScript, right? You trust it, but if, for example, the CDN gets hacked, the content of that JavaScript can change and can become malicious, and this is a vector for example, large-scale attacks or web worms. This has happened in the past, and a very simple mitigation against that is having some kind of integrity check of the content of JavaScript that you are including. So in supporting browsers, we'll have a table about that. It's as easy as adding an integrity tag, attribute to the script tag. You just do integrity and a SHA hash of the content of the JavaScript file you're including. So there are tools to compute the hash. You can go to, for example, srihash.org, or you just Google or Bing SRI hash generator. Cross-origin anonymous is actually not part of SRI. It's part of core specification. Just means that the XHR does not send credentials, because you also want that extra bit. So nowadays, if you look at, for example, jQuery, official web page, it will automatically ask you to copy-paste a tag that has SRI, which is really cool. We'd like to see this more adopted in the wild, because it's a very easy way of stopping these kind of attacks. So browser support for SRE is pretty good. I would say all real browsers support it. Firefox, Chrome, Safari, and New Edge. So that's, and of course it degrades gracefully for old browsers. So basically it just gets ignored. It's an attribute that gets ignored. So there's no drawback to actually use it. Same-site cookies are a very interesting mitigation against cross-site request forgery. So in cross-site request forgery attacks, basically when an attacker tricks the browser to send an authenticated request to a vulnerable website, the problem is that that request is authenticated. So it's sent along with the cookies of the user, even if the navigation is across sites, right? So it is from the embedding, let's say, evil.com that has an image or a form to vulnerablebank.com. And the idea is, what if developers could restrict cookies to actually be sent only if there is no cross-site navigation? So only if the navigation is same site. And the idea is to add a flag to the cookie called same site that could have two values, strict and lax. If you use strict, cookies are never sent when there is cross-site navigation. When there is lax, cookies are not sent when there is cross-site navigation and there is an unsafe HTTP method such as post. This means that, for example, if you receive an email on your Gmail or Yahoo Mail and you click on it, this is a GET request, right? And if you use strict, you would not send cookies at all. So, for example, your session would kind of disappear. So this might be surprising to some users. So you have to weight the two levels of security that strict and lax give. If you really have all the the actions with side effects that has post or put or whatever, then you can use lax, but the best would be to use strict. But then you have to take care into that. Basically, links, external navigation will have the user not logged in when they jump in your website. The support for same-site cookie is a little bit more limited. Firefox just adopted it, which is great news. Chrome has it for a couple of major versions, and unfortunately, there is no Safari nor Edge support. Let's talk about something different: site isolation, KORB, and from origin. So this steps out of the pure web world. This is not against web vulnerabilities, not against cross-site scripting or cross-site request forgery. It is mostly against, let's say, more low-level attacks. It is ensuring that pages from different websites get rendered into different processes in the operating system. This is done to isolate the renderer process in Chromium. Here we are mostly talking about Chromium only. This is because it's pretty much design dependent. Other browsers have a different way of using a renderer process, don't have a renderer process, or they have it in a different way, while Chromium it has a renderer process and then it has sandboxes. This goes one step further and basically says all the data, ideally, of one website has to be constrained and limited to one process. It also blocks the process from receiving sensitive data from other sites with some techniques. This can be enabled as a Chrome flag. You do Chrome flags, and then you search for a strict site isolation, and you enable it. It's not enabled by default. It will be probably in a while. It's not enabled by default because it used to break a very, very, very small percentage of websites. Mostly they were very plugin heavy. They had external plugins for their working, and they were not compatible with this strict process isolation. So why am I bringing this up now? This is might be surprising, right? Chrome has pretty good security already with Sandbox. Why we need extra isolation? Well, you might have heard of Spectre and Meltdown vulnerabilities. This makes exploitation on the web of especially Spectre vulnerability much, much harder. There are some theoretical exploits that try to put some attacker-controlled payloads, either as a resource, such as an image, or as a document, like HTML, in the context of a page, and then try to exfiltrate it by exploiting the speculative attack of Spectre. So this was reprioritized, and this became more important. So you might have read somewhere, if you use Chrome, enables strict site isolation to protect against Spectre. What is KORB? KORB is an important part of site isolation that basically restricts which cross-origin data is sent to a renderer process or a process, limiting the access to such data. An example is, for example, if an attacker, as I said, tries to load a document, like an HTML file that he controls, in an image tag, that would be blocked with KORB. This is, as I said before, mostly for mitigating against speculative side channel attacks like Spectre. This will be enabled by default. It will be part of site isolation when site isolation is enabled. There is another proposal that is actually pretty old proposal that now has regained steam. It's called From Origin. From Origin, very simply put, this is delivered with a header. So the two I said before, strict site isolation is a setting in the browser. This is a header, like content security policy, like the ones we'll see later. So from origin, basically a webmaster can put from origin to all the documents or the resources to prevent them from being loaded and included by known whitelisted origins. So I have a lot of images, and I don't want these images to be loaded from whatever.com. So yes, sure, this mitigates inline linking. Like there are even some attacks where bandwidth leeching, these kind of things. You could inflate the hosting bill of someone by just including in some high traffic forum or 4chan, all the heaviest resources that you have. But this goes even further in mitigating attacks such as Spectre. So it is interesting extra that is in the hands of web developers to restrict basically all the resources from being loaded from outside. So here are some upcoming mitigations that are not implemented yet, but that we would really like to see happening soon. And yeah, this needs, of course, let's say a full consensus from the community, the industry, W3, and every other actor. The first is suborigins. So suborigins are a pretty extensive and controversial, maybe, topic from an implementation point of view, mostly, not from a concept point of view. The idea is to subdivide the concept of web origin in a more granular way by adding to the web origin tuple, which is scheme, host, and port, like HTTPS, Google 443, a namespace that is provided by the webmaster, like accounts or user1. This makes it possible to isolate different applications that are running in the same web origins by not having to have a subdomain or a different domain. So there are some cool applications of suborigins, like per user origins. This would be they would provide extremely high security, both for cookies, for basically everything. You know, web origins are the foundation of web security. We rely on them. Making the concept of origin more fine-grained just automatically makes a lot of attacks harder and a lot of things more secure. Of course, it also makes it could create some problems. Can be used to segregate user content from the main origin. Let's say that, okay, so if you have user content, you should really use another domain, right? Like googleusercontent.com or githubcontent.com or the .io. But let's say you really can't and you have /usercontent/. Well, then in theory, you could use suborigins to make it so it's exactly like it was another origin. So that's very powerful. Another idea is sometimes you have sensitive functionalities on the same origin, like /admin. WP admin is WordPress admin, right? You don't want usually to be on the same origin of the main content, especially if you allow user content, you allow user uploads and so on. This would make it possible to isolate such sensitive functionalities easier. So adopting suborigins might require some refactoring of existing web applications. This is because there come to be more communication types. Suborigin to suborigin, suborigin to the, let's say, parent origin, and suborigin to an external origin. So in case of communication suborigin to suborigin, well, then the receiving or, well, the other page, the other document should just have declared the same suborigin via suborigin header. So this makes them both part of the same suborigin and everything works. If you want to communicate to the parent origin or to the origin in general, then you need the origin page receiver or sender, let's say endpoint, to add access control allow suborigin, which is a new header. There is access control allow origin, right? But there will be allow suborigin. Maybe. This is not set in stone, of course, this is being discussed. And suborigin to extern, the other endpoint should have access control allow origin. So here I would like to demo, Chrome extension that we created, an intern in our team, Elena Ionescu, called the Suboriginator. That it's good for testing and prototyping suborigins. So basically says if the website you are testing would work out of the box with suborigins, or if it needs modifications and which ones. So, yes. Let's go. We have this problem at Google. We have some Google services that are mostly for historical reasons on the main domain of Google, www.google.com. Of course, www is a very sensitive domain, and let's go to www.google.com/about. Okay, these are some static web pages that are updated frequently, and they often use different technology stack of what we use for our products. This means that there is a potential for them to have some vulnerabilities we are not aware of, and maybe we would not have on other products. And by being on the same origin, this means that a vulnerability, an XSS, for example, in these static pages would be as bad as having it in a major web application or in the account area. This is, of course, a problem. So let's see how it works. We open the Suboriginator extension. We put about as the target site, and we start it. Right, here we have a warning that Suboriginator is debugging this browser. And we just browse around a little bit. That's blog post about using machine learning to help stop deforestation. And let's just try to exercise the UI a little bit. Let's move this eye. Yeah, it's cool. And let's stop it and see the report. So these are the reported cross-origin requests. There are only suborigin to suborigin requests. So some MP3 files have been requested, then a video, and audio again, a TXT file. So as you can see, like a lot of resources are being requested, but they could be part of the same suborigin. So this means that it is as easy as adding the same suborigin. We could be about, for example, right? This means that basically this works out of the box. We don't see suborigin to origin, we don't see suborigin to extern. That would need to be refactored. So this is very promising, and this means that this would be pretty easy to implement. So let's stop this and let's go to another Google product. It actually redirected to search immediately. Just a second. Okay, Google Finance is becoming integrated with Google Search, and it's still on www. So let's do the same. Let's open the suboriginator and do www.google.com finance. We start it. Let's go around a little bit. This would probably go out because, yes, these are direct links to... Yeah, we can reload it. And let's go to... this is still finance. This is still finance. Okay, these are the indices, local market news, world market. Let's see what Suboriginator has to say. So in this case, we have a little bit more results. We see there are some suborigin to origin. This means that there are some requests from finance to the parent www/something else. We can see, for example, here, this is, probably some kind of JSON. This is probably all XHR-like things. This means that being a suborigin to origin, the origin would need to add the access control allow suborigin, like if it were cross-site request, right? Like with course, and suborigin to external. So we are sourcing content, loading content from play.google.com and ogs.google.com. This is mostly because of the bar. This is for the notification count of the bar on the top. So this will require not only modifications on finance, but also on these domains to add access control allow origin and access control allow suborigin. But this kind of tool, in my opinion, is very interesting. This is not open source yet. We need to, so this is very dependent on some, let's say, hard to update and to keep updated features of the Chromium API. So we consider creating an external version of this in the future, and but we wanted to show you a preview of what we have internally for prototyping such a technology. And suborigins are being discussed by W3, and there is some agreement, something on something people agree, on something people agree less, and we really hope to see this working and being implemented in browsers soon. Origin policy is another proposal. It basically pins policies such as the content security policy or referrer policy to an entire origin. So this complements header-based delivery and increases coverage by making it the default. So it's a little bit like HSTS, like mandating HTTPS on a whole origin. It actually says for the first time you query, you get a page from that origin. It says there is a manifest, and it says please apply these headers, these policies, automatically for the whole origin. So this is very good because sometimes there are different technology stacks and the coverage of, for example, content security policy is not perfect. Like maybe you have some kind of routing to, let's say, an error page or something like that, that is not completely in your control. I don't know, you have some weird load balancer that goes externally, you have F5, these kind of things. And this makes it the default. So it assures you that you have good coverage. This is also being discussed. Feature policy, which is also at a proposal stage, allows the administrated web admin to selectively enable and disable different browser features and web APIs. So the idea is you can say on my website, I don't want people to, I don't want to allow browsers to go full screen. I want to disable web USB on these pages because I don't use it, or so on. An example is in combination with origin policy, you can restrict geolocation API, like the ones to get the location, to a particular page, thus reducing the attack surface in case of an XSS on the domain. So we usually, as Lucas said before, we usually don't think about the post-XSS, like once you have JavaScript code execution, usually you can bypass all the mitigations. This would be one of those rare cases where this, in combination with origin policy, could actually reduce the capabilities of an attacker once they got XSS, because they couldn't, for example, exfiltrate the user position. We're done, I think, a little bit earlier. Hope you liked it, and if you have any questions.
So we're opening questions on the floor.
Thank you.
Any questions? All right. Thank you, Lucas and Michele.
Thank you very much.
All right.
Thank you.